So in environmental toxicology, we should study the effects of the hazards, right, that's available to us. So one way is the dose response analysis, which is the cornerstone of toxicology. Now the standard method of testing, right, with the lab animals in toxicology, we call it the dose response analysis. So that we scientists, we try to quantify the toxicity of a substance by measuring its strength of its effects, or the number of animals that is affected by the different doses. So we know previously that the dose is the amount of substance the test animal receive, and the response is the type or the magnitude of the negative effects that the animal exhibit as a result. The response is then, right, generally quantified by measuring the proportion of the animals that exhibit negative effect. And then afterwards, right, we collect all these bulk data in the data lake and we plot them across an axis on the graph. So normally we have the dose on the x-axis, horizontal axis, and then the response in the y-axis, right, something like this graph here. And the resulting curve is called the dose response curve. And once the scientists, analysts, statisticians, they've plotted this dose response curve, the toxicologists then will calculate a convenient shorthand gauge of a substance toxicity. Like they will determine the amount of substance that need to kill about half the population of the study animal use. So we call this the lethal dose for the 50% of the individuals. In short, right, LD50. This is a term that you can't escape from, or you have to know what is LD50, what it stands for, and what it means. So a high LD50 means you have a low toxicity because you need more amount, higher concentration of that chemicals to kill 50% of the population. And in turn, if you have a very small value for LD50 means what? I just need a little bit of the chemical, a very minute concentration that can diminish about half the population of the animal tested. So it's very tragic. Some substances can also elicit effects at any concentration, but generally, right, the response may only occur above a certain level, like we call it a threshold level. So we call it, in this graph here, a threshold dose, right? It might be expected if the body's organs can fully metabolize or excrete a toxicant at a low dose, but when you get too much of it, the body gets overwhelmed and they just store it, you can't excrete out at a high concentration. So this might also occur if the cell, right, that can repair damage to the DNA, only up to a certain point. So when we grow older next time, we find that our wounds will heal much slower because of the cell division is slower, our spindle fiber becomes shorter, so we should treasure our youth. Now there are other times, right, a response might decrease as the dose increase, although it sounds very counterintuitive, but it happens too. So the toxicologists, right, they find some of these dose response curves that are U-shaped, inverted U-shape, or J-shape, or like this. This very counterintuitive dose response curve often occurs with the endocrine disruptors, likely because the hormone system is very geared to respond to the small, minute concentration of the substance. In life, sometimes you think that 1 + 1 = 2. But that might not be true in environment. Maybe 1 + 1 give you 3, or 1 + 2 give you -2. So how does it work? The mixes may be more than the sum of their parts. Now it is very difficult to determine the impact of a single hazard, but the task becomes so difficult when there are multiple hazards that interact. So right, the chemical substances, right, when you mix them, they might interact in such a way that we cannot even predict them from the effects, each of them on its own. So when we mix toxicant, right, it may actually sum up each other's effect, or cancel out each other's effect, or even multiply each other's effect. So these whole new types of impacts may arise when different toxicants are mixed together, and these interactive impacts that are greater than the simple sum of their constituent effects are called synergistic effects. Now, we got 4 types of synergistic effects. Number 1 is your additivity, where it is a combination of 2 or more chemicals, the sum of the expected individual responses. So basically, it's saying that your normal mathematics, 1 + 2 give you 3, right? 4 + 4 give you, 8. And 3 + 2, 5. Chopsticks. Now, antagonism means you expose one chemical that will cause the other one to deflate. So it's like saying that the 2 effects, right, they cancel each other. Okay? So potentially I'm talking about 1 plus 2 give you 1, right? Suppose you get a 3 but then now become 1. Potentiation is exposure to one chemical that results the other chemical producing a greater effect than given alone. So imagine, right, you have A and this is B separately, right? But then you put A and B together, B give you a 4 factor. And lastly, you have synergism. So for synergism, right, this is the exposure of one chemical that causes a dramatic increase in the effect of another chemical. You might think that these two are rather similar, but later on in the graph, I'll show you the slight differences. So here, now, we are saying that, let's say, right, for potentiation, you have 0%, right? Chemical B, 20%. So it says that A now is not toxic, but when you put them together, then B become very toxic. Now for synergism, it's like when you have a low, very mild toxicity of chemical A and chemical B is much more toxic. When you put them together, then the effect is greatly enhanced, become 100%. So like I said just now, additivity means, right, you just add up the sum, no simple math, and antagonism means, right, there's some kind of a negation factor here. Using a graph to depict it, right, synergistic, okay. So now we come to risk assessment. Now under risk assessment and management, we need to have government policy. And when does the government policy decide to ban a chemical or to restrict their use, right, it generally follows years of rigorous testing for the toxicity. So the strategies to combat disease and other health threats are really based on the extensive scientific research. That's why we are in the university, we have research centers, we spend a lot of money in the people in the labs. But the thing is, the policy and management decisions also have to incorporate what? Money, right? Economics and ethics. When there's no money, there's no research. And all too often, you have to be aware that, right, these are the factors that will be influenced by the political pressure from powerful interest, by the subsidizers, by the people who fund the research, and the steps between the collection and the interpretation of this scientific data and the formulation of policy involve many people and the assessment and the management of risk. Recall the incidents where the people talk about the ozone hole, the scientists, once you mention the hole, right, people who do not study science, they will just imagine, oh, it's a big hole, right, we need to stop the gap, we have to do something about climate change. It is about how people use words and pictorial diagrams to portray an idea that might not be highly accurate. Now, we need to express the risk in terms of a probability, right? So when we talk about risk, we're exposed to risk, this kind of environmental health threats. It doesn't mean that, right, we might be affected by it. Why is that so? Because we have something called the statistics, we call base rate. Now, even if something's very harmful, but if you have a very low chance of happening, then the risk is low. Okay? So whenever you consider the severity, you also have to consider the probability, and you should multiply them together to have the final conclusion. Now, the risk measured by probability, right, it is the quantitative description of the likelihood of a certain outcome. The probability that some harmful outcomes, like injury, death, environmental damage, will result from a given action, event, or the substance expressed, the risk posed by the phenomenon. So please, next time when someone tells that this is so dangerous, this is so toxic, you have to tell them, are you having some base rate neglect? Are you ignoring just the probability and focusing all on the severity? Now, every day, we have to take decision, and every decision that we make involves some elements of risk, right? Normally very small, that's why we're here today, we are alive, right? Unlike the tribal past where people are always exposed to danger around them. Now, there's a low probability that things will go wrong. So in life every day, we behave in ways that will minimize risk, because humans are born in such a way that, right, we like to preserve our livelihood, we like to survive and pass on our genes to the next generations. So we do not have to worry about small risks that will affect us somewhat, but sometimes we like to engage in activities that's a high risk, like what? Jaywalking, right? Running across the streets. All these are actually high risk, but are we even realizing that? Now, for example, something more severe would be, right, people like to think that, oh, flying aeroplane is riskier than driving a car. But if you look at the history and statistics in a 2012 report by the National Safety Council, now a person's chance of dying from an automobile accident, if you're driving, right, or you are the passenger, is about 73 times higher than from a plane crash. But the thing is, psychologists also agree with us that this difference is about the perception of people, because when plane crash happens once in how many months, right, it is so big, it is so severe, you see a huge flame blowing up in the sky, it's so scary. Compared to a car or vehicle that blows up, right, which one is more impactful? So we have to differentiate between perception and reality, right? And this stems from the fact that we feel more at risk when we are not controlling a situation, and we feel more safe when we are at the wheels. So imagine we are driving, right? We think we are controlling a steering wheel, but how many times do you know that road accidents are caused by the malfunctioning of the car? That means, right, you are the driver, right? And then you drive very safely, but the car become locked or become old, and there's some malfunctioning which is not within the driver's control. Now, risk assessment also analyzes the risk quantitatively. So how do we quantify the measurement of risk? So we need to compare the risk, right, with different kinds of activities and substance together. We call it the risk assessment. And there's a few ways that we can do it. Risk assessment is one way to identify and to outline the problems. Now, in environmental health, right, it helps to ascertain which substance and activities pose health threats to people or to the wildlife, and to which they are largely safe. So the key main steps of risk assessment. Number one is the hazard identification. What kind of hazard? Electrical hazard, fire hazard, chemical hazard. Next is the dose-response relationship. How much is needed to cause a severe damage in the health system? And next, exposure assessment. How likely are we, or the people involved, are exposed, will encounter this kind of risk? And lastly, risk evaluation. So normally, we would like to multiply a factor 2 and 3 and then get the number, and then we set some numbers as a framework to see whether it is scored highly dangerous, do not proceed, or mildly dangerous, or low risk.